Hello everyone. In this video, I'm going to be discussing a concept that no chemistry student likes, but unfortunately everybody has to learn it, especially if you're in the chemistry lab. These things are always going to be counted, at least for some type of grade. And so whenever I talk about numbers, you think you understand numbers until I just throw all this information about you, and then you realize you didn't know as much as you thought you did. So the first thing we have to talk about is significant figures. And so significant figures are something that, again, you're really going to learn to hate, but you need to pay attention to them. And so every measurement that is going to be taken, either in a lab or given to you at some point, when you see it written out, it's going to have some uncertainty to it. What I mean by that is most of these devices we use are man-made. And of course, men make mistakes. And so if humans make mistakes and mistakenly humans make these instruments, they're going to have some type of issues with them. So when you see these numbers written out, the rightmost digit is always going to be your estimated digit. What I mean by estimated is even if your like digital scale that's giving you the measurement and you put a object on there and the scale says 7.5 and that 5 changes to a 4 and then back to a 5 and then back to a 4. It just basically, even the instrument doesn't really know exactly what that number should be, so it's kind of estimating that last value. Or if you're looking at a graduated cylinder, if your liquid is between two numbers, you can't really tell me if it's on like the 13 or the 14. You have to give me an estimated digit to tell me where that liquid actually sits. And so whenever you see these numbers written out, they're always going to include your certain values, the values that the instrument can tell you specifically, and then a one and only one uncertain value. And so the uncertain value kind of depends on what instrument you're using. And so if you write these values out correctly, your certain information with one and only one estimated digit, this is what they refer to as your significant figures. And so the great thing about your significant figures is if your value or your instrument gives you more sig figs, then it's basically telling you that that value or that number that you gathered is probably going to be a little bit more certain than one with less number of sig figs. And so I'm going to give you a heads up now. There are a lot of rules here, but they are not as horrible as they look at first. And with a little bit of practice, you'll become an expert at this. And so, when it comes to measuring devices, the rule of thumb is always to estimate one digit past the smallest tick mark. And what I mean by that is if you take a look at this graduated cylinder here, you'll notice between 50 and 60 there are 9 lines. And so we know that this is 51, 52, 53, 54, 55, so on and so forth, 59 to 60. And so here, the smallest tick mark, or the smallest increment that it goes up by is 1 milliliter. And so if we were to read the value of this liquid, again, by the meniscus, if you guys don't know what a meniscus is, it's whenever the water kind of dips down a little bit, you always read from the bottom of the meniscus. And so if you read this value here, you can tell me that this is above 52. We know that because this line right there represents 52 milliliters. But in this case, it's not quite at the 53 yet. And so because it's not on the 52 and it's not on the 53, you can't tell me either of those numbers is correct because, again, you're not going to give me the exact information I'm looking for. And so if you say 52, you're under what it's supposed to be. If you say 53, you're over what it's supposed to be. And so in these cases, you have to give me an estimated digit. And so in this situation, you can tell me that because it's between 52 and 53, you can tell me the value or you can write the value down as 52.5. But the main thing is here is even like scientists who have been in the field for 50 years, they really don't care what that last digit is. It can be a 0.5, 0.3, 0.7. The main idea here is they need to see a value in that 0.1 spot or in that 10th spot in order for this to be considered accurate. And so please note here, I did not say it's 52.50 milliliters. You can only estimate one digit past the smallest increment. And so if I say this is 52.50, I'm telling you that my eyes are so awesome that I can tell you that that line right there is 51 hundredths of the way between the 52 and 53. I do have good vision, but it's not that great. And so here, one digit past the smallest increment. So this might change depending on your instrument. And so if you kind of take a look at these two thermometers here, both the thermometers are measuring the same value. But because one of them is going to be going by 0.1 degrees Celsius, the other one is going to be 1 degree Celsius, your reported value is going to be different. And so if you take a look at the one on the left-hand side, and to make things a little bit more clear here, here's a red line. And so here you can look and you can see that these values kind of going here from 32 to 33, and there's 9 lines there. So you know this 32.1, 32.2, 32.3. And so that line right there represents a specific value of 32.3. We know that is certain because that value or that line exists there. And so we can write out our 32.3 as our certain values. But because it's not exactly on that 32.3, we need to give one additional estimate here and say 32.33. And so, kind of a side note here, if that line were directly on that 32.3, you would still have to tell me an estimated digit. And so you would write that as 32.30, because again, if you were to write it out as just as 32.3, then you would be kind of doing something similar to the instrument on the right-hand side. And so on the right side, you'll see that the measures or the increments are 1 degree Celsius. So the same measured value, the same temperature, but here, because we're going from 30 to 40, and there's 9 marks, this line represents 31. That's 32. That's 33. And so here, the only certain value, the most certain we can get with this instrument is 32. But again, because it's not right on that 32, we have to say 32.3. We have to give an estimated digit. But please note here, you cannot say 32.33 for this one because that's too much estimating. And same note on this side, you can't just say 32.3 because if you did, if this was just 32.3 and nothing right there, you would be implying that only the 32 is certain and that 0.3 is estimated. So that's why if this one was right on the line, you would still have to tell me 32.30 because that 0 is going to be your estimated digit saying, I think it's really close to that line. So, get ready for these rules. Take a deep breath, let it out, you'll be okay. Sig Fig rules, there are a lot of them, but they're not as terrible as they seem. And so just kind of bear with me and I'll walk you through each one of these rules here. And so the first rule should be the one that makes the most sense. All non-zero digits are significant. Meaning the fact in this 28.03, that 2, that 8, that 3, all of them are going to be classified as significant. And so any number, 1, 2, 3, 4, 5, 6, 7, 8, 9, are always going to be classified as significant digits. And so in this one, I'll talk about the rules here in a little bit for that 0, but your 28.03 has 4 significant figures. That's 54 or 0.0540, which again will make sense here in a little bit, has 3 significant figures. The main thing I want to point out here is that 2, that 8, that 3, that 5, that 4, all of those are significant values. So interior zeros. So these are zeros that I personally refer to as trapped zeros. And so in the case of 408, that 0 is trapped between that 4 and that 8. Those 4 and that 8 are going to be significant values because they're non-zero digits. And so that 0, it can't escape. It has to be counted as well. And so same as that 7.0301, that 7 and that 3 and that 1, those are significant digits. So all of those have to be counted. And so those zeros trapped in between them, they have to be counted as well. And so the last kind of easy rule to kind of explain here is the leading zeros. And so leading zeros are the only one on this slide that are not significant. And so whenever I mean not significant, I mean they are not counted as significant values whenever you're reporting these values. And the reason for that is going to be, up here, forgot the 408. So 408, 3 sig figs, this has 5 sig figs. Apologize about that. And so in this 0.0032, if you kind of take a look at this value, those decimal points, again, they kind of throw you off a little bit. But if you just kind of think about the number 13, and so the number 13 is written out as 1, 3. No matter if you throw 16 zeros in front of that 13, that number is still 13. Throwing all those zeros in front of it's not going to do a damn thing to change the value of that number. And so if you have leading zeros, all they really do is just kind of tell you the position of the decimal point. And so if you have a bunch of zeros in front of a whole number, they're telling you that that decimal point is nowhere in front of that number. But if you have the value like 0.0032, those zeros in front of that 32 are just telling you, hey, there's a decimal place 2 positions before this number. But you can actually rewrite that value as 3.2 times 10 to the negative 3, and it shows you the exact same relationship here. And so any zeros in front of your value, if there is no numbers before, are always going to be considered non-significant. And even again, with that 0.0000, I lost the numbers of zeros, but point with a bunch of zeros in front of it, and then a 6, that 6 is the only significant value here. And so even though there's a bunch of zeros all around these two numbers, and at 0.0032, there's only 2 sig figs. That 3 and that 2 are the only ones that count. Same deal with this other one. That 6 is the only value that actually counts here. And so, Rule 4 is broken up into a couple different bullet points, mainly because trailing zeros have their own issues. And so trailing zeros are zeros that come after your value. And so trailing zeros after a decimal point are always going to be counted. And so going back to my previous example with like the 2 thermometers, the one that has the increments of 0.1 is always going to give you a little bit more accurate answer than the one that has the increment of 1. And so in this case, it's telling you the more significant values you have, the more precise your answer. Another way to look at this is scientists, when they spend all of their money on all their instruments, they want to buy the latest and greatest instrument. And not only that, they want to show it off to all the other scientists saying, haha, look what I have. And so basically, you are paying for these zeros. A more expensive instrument, a $5 million instrument, will measure out to like the 6th decimal place. If you have the $500 instrument, it may measure out to the 1st decimal place. And so in this case, the more zeros you have, the more important those values are, because they tell you that in this example, the 45.000, it's telling you that that 45.00 is for certain your instrument measured out to the 2nd decimal place. That last zero or that 3rd decimal place is going to be your estimated digit. And so here, you're saying that you know your value is for certain above 45.00. And if you have an instrument that is, again, $500, you can only tell me that 45 is certain and that 0.0 is your estimated digit. And so for that reason, all trailing zeros after a decimal point are always going to be significant, even if there's not another number that follows them, if it's all zeros. So trailing zeros before a decimal point are where you kind of run into issues. If you have a trailing zero before a decimal point, but there are numbers in front of it, then all of those are going to be significant. And what I mean by that, there's a difference between this 0.0032 and this 140.00. Say that in front of this there is a 3. In that case, then yes, all of these values would have been counted. If this was 3.0032, then you'd have 1, 2, 3, 4, 5 significant values. But because there is no number, like real number, a significant value in front of this decimal point, it doesn't count. But here, you have 140.00. Because that 1-4 is sitting there before that decimal point, then all of the zeros that are like trailing afterwards are going to be counted. And same deal, even if you have them trapped here, these are still going to be kind of like trap zeros, so those have to count. And so trailing zeros before a decimal point, but they have to be after a non-zero or after a significant value to be counted. And this second to last bullet point, actually these last two bullet points kind of go together. So I will never try intentionally to mess with your brains unless that's part of the problem. And so some number is like 1200, like this value ran out as 1200, depends on what book you pick up. And so some books will tell you that that has 2 significant figures. Other books will tell you that it has 4 significant figures. But me, I just won't do that to you because I have no idea, depending on what instrument you use to measure that value. And so in order to kind of get away from ideas like that, I would write most of my values out as 1.2 or 1.20, 1.200, to specifically tell you how many sig figs I'm looking for. And so any number that doesn't have a decimal place at the end, it can be counted if you do something like this. So if I want this 1200 to be counted with 4 significant figures, I would write it as 1200 with a decimal point with nothing after that. And so this is going to have 4 sig figs. And so please note, I did not write this as 1200.0 because then again, that would make this as 5 sig figs. And so in a value like this, I'm telling you that this 1, that 2, and that 0 are going to be my certain values, but the instrument I used went up by like tens, and so this 1 is going to be my estimated digit. And so when you kind of go through and look at these, going back up here, I kind of jumped over them because I wanted to explain all of them first. But if we look at this 45.00, those trailing zeros count, and so we're looking at 5 significant figures. This 3.5600 with trailing zeros, all those zeros after a decimal point, and they have significant values in them, you can be looking at 5 sig figs. And so here are 140.00, that 0 right there, 1, it's trapped between that 4 and that decimal point, so you can kind of call it a trap 0. But additionally, all the zeros after the decimal point and before the decimal point are going to count if there is a number in the front there. And so here you're looking at 5 significant figures at 2500.55. These are, again, trap zeros. They're before a decimal point, but there is a number beforehand, so all of those values are going to count for 6 sig figs. So let's do some practice. If we have a value of 0.000407, and so I want to know how many sig figs this is going to have. So the first thing you have to ask yourself is, what rule does this fall under? And so in this case, that does have a trap 0, but that's not the more important one. The more important one is that this has a whole bunch of leading zeros, which don't really mean anything as far as you're concerned. In order to prove that, you can actually rewrite this thing out as 4.07, and that value will show you that you're going to have 3 significant figures. And so you want to write this out as 0.000407 times 10 to the negative 4. This next example here, we have 7.0009. And so first off, zeros after a decimal point are always going to be considered significant because that's basically telling you, hey, I bought the more expensive instrument. In addition to that, this 9 on the end is going to basically make these zeros trapped or captive zeros. And so here you're going to have your 7 and your 9 definitely going to be considered significant. And all those zeros are going to be trapped there, so you're going to have 5 significant figures. And so you're 1090000. And so in this case, notice that there is no decimal point. And so because there's no decimal point, it's telling you that you are going to be looking at a value that is just going, excuse me, that's just going to be a bigger value. But as I stated earlier, you can again kind of take a look at these trailing zeros with no decimal point and realize that they're insignificant, and this is going to have 3 sig figs. Just to verify that, if you rewrite this in scientific notation, you would write it out as 1.09 times 10 to the 6th. And so when you kind of take a look at this, you ignore all those zeros at the end because it is just telling you, like, hey, the decimal point is all the way down there. But the 109 is the only real significant portion of this, that number. And then the last one, if we have a value like 15,000, but I have a decimal point there. And so that decimal point after the trailing zeros is telling you that all of those zeros are going to be significant because my, again, certain value is going to be in the 10 spot, and that one spot is going to be the estimated digit. And so for this one, you're going to be looking at 5 significant figures. So something that's special about this guy is if I'm telling you those zeros are significant, you can't get rid of them whenever you convert this into your scientific notation. And so this 1.5000 times 10 to the 4th is how you write this one out in your scientific notation form. And so these numbers are all well and good, but unfortunately for you, your whole job is not just going to be looking at numbers. It's going to be messing around and playing with these numbers. And so when it comes to doing calculations with these numbers, there are 2 rules you need to commit to memory right away. And so the first rule has to do with multiplication and division. When it comes to multiplication and division, the smallest number of significant figures is what's going to limit the final answer. And So what I mean by that is you need to figure out the number of significant figures in both of your values, and the smallest significant figures is what you have to round your final answer to. So if you look at this first example of our 4.242 times 1.23, and so 4.242 has 4 significant figures in it, and your 1.23 has 3 significant figures. And so in this case, your final answer needs to be rounded to 3 significant figures. And so our 5.21766 is going to be rounded up to 5.22. And the next one, the one below that, we have 2.7832 times 1.4. So this first value has 5 significant figures because they're all non-zero. Second one has 2 significant figures, meaning the fact that this final answer needs to be rounded to 2 sig figs. So we're going to cancel out this 9648 and round up. And so our final answer is going to be 3.9. Please note, it's not going to be 3.90 because that is 3 significant figures. We only want 2. And the last one here is just showing you, even if you work with division, same rules still apply. And so the 2.3476 has 5 sig figs. Your 5.67 has 3 sig figs. And so your final answer here, again, needs to be rounded to 3 significant figures. So multiplication and division, significant figures is what rules the final answer. On the other end of the math scale, we have addition and subtraction. And so in addition and subtraction, basically, you can't have any more numbers in your final answer than you did in either of your beginning numbers. What I mean by that is you cannot have any more decimal places that didn't exist. And so if you take a look at this first one, this 12.5 plus your 2.567. So the thing you kind of have to ask yourself is, what is this 6, 7 being added to? And so you can't say 0 because there's no zeros there. And so the question is nothing. And so you can't add anything to nothing. It just doesn't work that way. And so here, you basically have to just kind of understand that those don't exist. They can't exist because the number that you're using has no other values to add that to. And so for addition and subtraction, I just ask you to channel your elementary self. When you were first being taught math and your teacher told you to line up all your one spot and all your decimal places, do the same thing here. Just line up your values and figure out which one has the smallest number of decimal places. And so here, that 12.5 only has 1 decimal place, so your final answer has to be rounded to the final decimal place and rounded up from there. And then our next value is the 12.5678 and the 0.12. You notice that your 0.12 only has 2 decimal places. That means that you have to cancel out the rest of the decimal places from the first value and round your final answer to 2 decimal places. Even if you're dealing with 3 values of adding or subtraction, same deal applies. Look for the one that contains the least number of decimal places and round your final answer to the least number of decimal places. So, just to be clear before we move on, multiplication and division is looking at the smallest number of significant figures. Addition and subtraction is looking at the least number of decimal places. When you get to addition and subtraction, your significant figures don't really matter any. It's only for multiplication and division. And so, that would be all well and good if you only did one type of math all your life. But unfortunately, again, life is messy. And so, when you deal with a mixture of calculations, the first thing you have to remember is your basic algebra skills, what to do first and things like that. And so make sure to do the parentheses first and multiplication and all that stuff before addition, all those rules. But the first thing you look at when you look at this problem here is I have a mixture of multiplication and subtraction. So the problem comes is that subtraction and multiplication have completely different rules. And so what you have to do is before you switch your rules, you have to stop, round your answer according to the rules you just did, and then you can move on to the next step. And so what I mean by that here is in this problem, we know inside parentheses we have our subtraction, and so we need to do subtraction first. And so the rules of subtraction are looking at the least number of decimal places, not sig figs, but decimal places. And so just to take a look here, our 782.3 has 1 decimal place. Our 451.88 has 2 decimal places. And so not just to confuse everybody, but here we go. I rewrite it on the other side so I can line them up. And we again see that our 782.3 minus the 451.88 needs to be rounded to 1 decimal place because the rules for addition and subtraction focus on decimal places, not sig figs. And so my second bullet point up there states to always carry a few additional sig figs. And what I mean by that is even though my number 330.4 is the only significant portion of that value, there is a huge difference between multiplying your 3.8900 by 330.4 and by 330.42. And so whenever I'm telling you to round your value according to the rules, I mean that. Figure out which ones are significant, figure out what values are actually going to carry through, but you need to keep that number the same. You need to keep the exact number carried all the way through in order for this answer to come out correctly. And so, I don't care how you do it. You either write down the answer and circle the sig figs or box them or bold them, however you need to do it. And so what I'm trying to say in the long run here is 782.3 minus 451.88 results in 330.42. That's what your calculator will tell you. But your calculator doesn't understand that this 8 is not significant. It can't be because it's not being added to anything. And so use the value that it gave you in your calculator. Write down 330.42, but make special note in the whole scheme of things, only this 3, 3, 0, and 4 are significant. And so when we take this, we're going to take this value of 330.42 and plug it into our parentheses. So here we have our 3.8900 times 330.42. The reason why we stopped and rounded everything is because the rules for subtraction are different than the rules of multiplication. And so here now we have to switch up our rules and look at significant figures. And so our 3.8900 and our 330.42 are now, abiding by different rules. Because our 330.42, only those 4 values are significant, only the 330.4 is significant. That's why the rule kind of changes here. And then our 3.8900 has 5 significant figures. And so our final answer needs to be rounded to 4 sig figs. And so our 1285.3338, which is what your calculator would have given you, needs to be rounded to 285. And so here, please note, if you did not stop here and do this rounding appropriately, you would have ended up with 330.42, and then you would have said 5 sig figs, 5 sig figs. This answer would have been rounded to 5 sig figs. And so even if we switch it up and change the order of the operations here, so if I have 4.58 divided by 1.238 minus 0.578, we know we need to do the division first. And going by the rules we've discussed, division looks at the significant figures. So here we have our 4.58 has 3 sig figs, our 1.238 has 4 sig figs, and so carrying this over to the side to make less room here, if you plug this into your calculator, you're going to get 3.699515. But again, the rules of division tell you that smallest number of sig figs will dictate how your final answer is rounded. So that 3.69 is the only significant values in that entire number. But as I stated previously, carry your entire number over in your calculations, because 3.69 minus 0.578 is a lot different than 3.699515. And so you carry the number, making special note that only there's 3 sig figs here into this next step. And so if we look at this now, looking at the way it's set up, we are now looking at subtraction, so we're looking at decimal places. And even though our number of 3.699515 has 1, 2, 3, 4, 5, 6 decimal places, these last 4 are insignificant. They don't count. And so here we're looking at our value has 2 decimal places. This one has 3 decimal places. So our final answer is going to be rounded at 2 decimal places, or 3.12. So again, I know these can seem confusing, but one thing I highly suggest when you work these problems out is do it kind of like I did. Do it step by step, making sure that you're rounding after every step that you're changing your rules. And so in addition to that, if you are dealing with dimensional analysis is nothing but multiplication and division all the way throughout the problem. There is no need to stop and round after every single problem or after every single step. And so if your calculation involves only multiplication and division or only addition and subtraction, then you are fine. You don't have to go through and start working out all this different stuff. But if you have a combination of division and subtraction and addition and multiplication, then you have to stop after, not after, you have to stop before you change your rules. And so, these last two slides, again, it shouldn't really seem too scary about numbers, but just to kind of give you a better definition of what type of numbers I'm talking about. And so, numbers you should all be familiar with, but the types, it's probably something you never really thought about. And so when we talk about exact numbers, we're talking about things you can count with your fingers and your toes. And so every dozen of eggs comes with 12 eggs in it. If we were in actual classroom still nowadays, then again, I can count the number of students I have with my fingers. Or if you look inside of a electron microscope at an atom, you can count the number of electrons. In addition to that, conversion factors within the same system. Please note my underlined words there. So conversion factors within the English system or conversion factors within the metric system, those are going to be considered exact. And so 100 centimeters in 1 meter, 50 to 80 feet in 1 mile. And so centimeters and meters are in the same system, miles and feet in the same system, inches and feet in the same system. And so conversion factors within the same system are considered exact. But conversion factors between English and metric are not. There is only one metric to English system that I want you to be familiar with as exact, and that's the one that I told you to memorize at least 3 times in these last videos to memorize. And so that 1 inch equals 2.54 centimeters is the only conversion that we're going to classify as exact conversion. Every other value that we're going to be dealing with throughout this semester is going to be called a measured number. And as the name kind of implies, it's a number that is obtained from a measuring device. And so again, it can be a scale, it can be a thermometer, it can be anything, or a mass spectrometer. Those numbers are going to be measured some way. But as I mentioned with measured numbers a couple of times throughout this video, measured numbers have uncertainty. And so again, whenever you talk about these measured numbers, you have to understand only some of those are certain, and that last value is going to be the estimated. And again, unless you really don't know how to count, you can't have estimated numbers and exact numbers. And the last bit we have to talk about with Chapter 1 is the difference between precision and accuracy. And so accuracy is always going to be a measure of how close your value is to what it's supposed to be. And so precision is going to be a measure of how close your data points are to each other. And so again, accuracy has to deal with the actual value. Precision is only going to be concerned with the data points that you're collecting. And so a great example of this is if you imagine a dartboard. And so if you have a dartboard in front of you and you are given 3 darts and you're aiming for the bullseye, if you hit all 3 of those bullseyes, then again, your values are accurate, your throws are accurate and precise. Because you're aiming for what you're trying to, and you hit it, and all of your darts hit what they're trying to. But say that you have your darts, and you're aiming for the bullseye, and all of them hit the 20. And at that case, again, you are not accurate. Your darts did not end up where they're supposed to be going, but they are precise. All of your data points are close to one another. All of your darts are kind of good grouping. But say that you are horrible at darts, and you throw your 3 darts, one lands on the 20, one again lands on the 2, and the other one lands on the ground. And so in that case, you're just terrible. You have no accuracy, you have no precision, and you should just stop playing darts altogether. And so when we kind of talk about these, again, accuracy is the measurement of how close your value is to what it's supposed to be. If you have a 10-gram sample and you put it on a scale and it says 10.01, then it's pretty accurate. But if you have a 10-gram sample and you put it on a scale and it says 13, then it's not accurate. And so the easiest way to figure out if a group of data points are accurate is just to take the average of them. If the average comes out to close to what it's supposed to be, then your values can be considered accurate. Precision, on the other hand, is how close all of your data points are to one another. And so if you have this 10 gram sample again, and you put that sample on the scale and it says 13, then you take it off and it says 13.1, take it off, put it on and it says 13.02. In that case, none of your values are accurate. None of them say the 10 grams are supposed to be, but they're all close to each other. And so precision talks about the grouping of your data points. Accuracy talks about how close they are to the actual value. And so the last thing we're going to discuss is errors. And so random error is an error that happens, again, equally up and down, or equally, again, off in either direction. And so what I mean is if you have that 10 gram sample and you put it on a scale and out of nowhere an earthquake happens. But instead of you running with the rest of the crowd, you really want to get those masses. And so you keep trying to get the mass during the earthquake. But that scale is going to read for that 10 gram sample. It's going to go to 2 grams, then up to 25 grams, then back down to 7, and then back up to 13. And so a random error, you have equal probability of either being way above what is not way above, being too high or too low. Whereas systematic error, these can usually be attributed to a broken instrument. And so that instrument or that scale I was talking about earlier, when you put your 10 gram sample on it, and every time I told you 13, that is a systematic error. Because again, it's always going to be off by that same amount every single time you use that instrument. And so a systematic error is always going to be either too low or it's always going to be too high. Random error bounces up and down. Systematic error is kind of a flat line, but it's a flat line either on top of where it's supposed to be or below where it's supposed to be. So that's all I got for Chapter 1. Hopefully you checked out all the other videos. If not, I always suggest doing so. And here's waiting until Chapter 2 pops up.